This conference will now be recorded.
All right, guys, let's settle down.
So, so we'll start with the PCIe and NVMe. So I didn't had a chance to merge both the presentations, but I will try to give you an overview of what we'll plan as part of PCIe and NVMe training. Uh, so we'll be focusing on Gen 1 to Gen 4 speeds. One thing, I mean, before I start off, one thing I want to talk about my presentations is I generally try to keep it as much verbose as possible. My presentations. I don't keep bullets like 5, 6 bullets and explain. Uh, I have my own reason why I do that, not because I want to read out from that. Because when I look back after, I mean, like I'm doing NVMe training today, my next batch might be 2024 or 23. So for me also it becomes a starting point where I can teach without again redoing the whole work. And when I share this presentation with you, you have the lot of content available where you can easily connect the things rather than again looking at bullets. So that's the reason where most of my presentations are very verbose. I try to put as much information as possible into the presentation. Right? Now, it's not just going to be, I mean, coming back to our demo, I mean, the session that is being planned for today, it's not just going to be about PCIe. It's going to be about NVMe and how PCIe are connected, where they are connected, what is NVMe, and why we need PCIe Express in that context. And now, coming to the PCI Express, what will be covered is the course will be majorly protocol training focused, majorly. But as I said, I am not going to teach what I know. We'll try to align it again specific to your requirements. Like we will have some part of the training focused towards learning the debugging aspects of the PCI Express and NVMe, and how to do the validation. I mean, what are the concepts, analyzers, those kind of things also we'll get into. Right? We will be majorly focusing on Gen 1, Gen 2, Gen 3. Actually, if you when we go into PCI Express, you will see that there is a major update that happens in Gen 2 to Gen 3. In USB, the major update happened from 2.0 to 3.0. I mean, the overall architecture, everything changes when you go from 2.0 to 3.0. That is where you see that we were moving from the speed of 480 megabits per second to 5 gigabits per second. In PCI Express, that change, major change comes Gen 3 to Gen 2 to Gen 3. Again, the training would and other thing is in PCI Express, those layers are called as transaction layer, data link layer, and physical layer. In USB, we call them as protocol layer, link layer, and physical layer. And so they in all these generations, Gen 1, Gen 2, Gen 3, Gen 4, even Gen 5, you don't really see big differences between protocol layer and data link layer. You don't see much change. Most of the changes happens in physical layer. And we will also be talking about PCI Express 5. I don't think this may not be probably relevant for you, the controller test plan and those. I mean, this is a generic presentation which I use even for my regular trainings. Okay. And I'll be sharing all the material to you, the specifications you will definitely have, the notes and some presentations will also be shared with you. So this is all what I plan to cover. But during this session itself, I'll be trying to connect the NVMe with PCIe. Talking about PCIe technology training agenda, we'll be starting off with understanding of the PCIe protocol overview, the architecture, the PCI Express configuration space, the enumeration, address space and transaction routing. Then we'll go into individual layers. So where we'll start off with understanding the transaction layer, we'll start off with understanding the data link layer. Then we'll talk about physical layer. Then finally we'll talk about the other aspects like we'll talk about the interrupt support, error detection handling, power management, and pipe architecture.
Just check the connect.
Now, before we get into it, let us understand how PCI Express and NVMe are connected. Okay. For that, we have to get back to the storage technologies, right? Storage technologies. I mean, you are the experts, but I can still give you a brief about what is storage technologies. You know that there are two types of memories, right? One is volatile, one is non-volatile. What is volatile? Something that holds the values as long as power is applied. Okay. And other type of devices are non-volatile, which hold the value even after power is removed. Right? What is an example of a volatile memory? RAM, DRAM. These are all examples of volatile memory. What is an example of non-volatile? Flash, ROM. These are all examples of non-volatile memory. So in non-volatile memory, our target is to reduce the footprint, and I mean, idea is to reduce the footprint and reduce the cost per bit of the manufacturing, right? So that is where we have two types of technologies, where we have hard disk drives and solid state drives, right? How does hard disk drive work? You have a storage, I mean, magnetic based thing, rotation technology, through which you detect the bits whether 1 or 0, right? And then we have a new technology that is being used, which is solid state drive, where we use the two kinds of technologies. One is NAND flash or NOR flash. When we go deep, I mean, when we start off with the NVMe training, there we learn that what is the difference between NOR flash and NAND flash. You will realize that NOR is good at reading, I mean, it's quick to read, but to write and to program, it's slow. But NAND is good at writing. And from the second point, NAND is more efficient in terms of the memory footprint. I mean, you need to store per bit, you need more space for NOR flash, less space in NAND. That's a very brief about what we are talking. And you know that how the SSDs are manufactured. They are manufactured in a whether you take NAND or not, the data is stored into a MOSFET uh, through a charge trapping technology. That's where it all comes down to. Then you are all aware about how the SSD is being implemented. It is being implemented as pages. I mean, you have bit cells, which group of them constitutes the bit cells, and you have rows and multiple such things being stacked. There is a terminology which we'll talk about, right? The rows, columns, and the bit line, and the gate, which is, I mean, the common gate line for each of the page. What is the concept of page? Everything we'll talk about. Now then, I mean, once you connect this device to the laptop, it all comes down to how quickly we can read that information. I mean, we can do writes and reads to that storage device. That is where we have started with the technologies like SATA, then we have SAS, then we have moved to a new technology which is PCI Express based SSD. We had SATA based SSDs, SAS based SSDs. Now we are talking about PCI based SSDs. Where does the basic difference comes is the number of commands. I mean, SATA and SAS are squeezy, they call SESI, right? They are all more hardware implemented protocols. I mean, a lot of things goes into the hardware, less load onto the drivers. When you come to SSD technology, SSD technology, most of the load goes onto the drivers. Where in case of SATA, it supports only one channel, where you can place one queue with 256 commands. Whereas when we go to SSD technology, it supports up to 64,000 queues. Each queue can have up to 64,000 commands being placed. Now each command, when we say command, the command itself will be two categories. One will be either it could be administrative command, it could be NVM set command. So I'm sure some of you has familiarity with these concepts. Now the whole idea is all about how this exchange happens. I mean, how does this command will be processed by the NVM controller? So what we will do is how does NVMe and PCIe fit into the overall system architecture? Let's try to understand what is NVMe, what is PCI Express. I mean, why are we not using NVMe itself? Then what is the need for a PCI Express? Let's try to understand. So far, what we did, we just took a very quick overview of what is SSD. This is my system. If I connect a device which is based on PCIe interface, for example, I'm connecting a PCI based SSD device. Here, let's say I have a processor. So I'm not showing the motherboard and everything. What happens is the SSD device would be 4 pins, I mean X4. So we would insert it into my motherboard. So there will be a motherboard, let's say with PCI slots of, let's say 24 slots. 24 lane slot is there. I would connect it into 4 slots of my PCI. So I'm using basically PCI slots to connect my SSD device. Here, where does NVMe comes into picture is, here on the SSD device, there is something called as NVMe controllers. The controllers will be there. The controllers can be two types of controllers. One is called as administrative controller. One is called as IO controllers. So that constitutes my SSD device, and this part of the storage device is the SSD storage. The whatever stacks we talked about is what. So my SSD device can be divided into two parts. One is the controller related portion, where it can be two types. Actually, it's three types. It can be administrative controller, it can be IO controller. The third one can be discovery controller, which is not related to PCI Express. So for now, since we are talking about NVMe with PCI Express, so for us, two types of controllers are relevant. One is administrative controller, one is IO controller. Now the question comes, where does PCI fit into this overall architecture? Okay. So in this case, what happens is, again, assume that this is my laptop. When I initiate an application, any questions? 24 is the lanes. My PCIe and motherboard slot can be supporting 32 lanes, or it can be supporting 24 lanes. Out of the 24 lanes, I'm going to consume 4 lanes for SSD connection. My SSD will have 4 lanes. So those 4 lanes will be inserted into it. These remaining 20 lanes can be used for some other connections.
I think X16 is max. X24. X16 is the max.
16. Okay. No, up to 32 it can support, right?
32 lanes.
30, yeah.
But what I'm saying is there is no.
Okay, sorry, then it's a correction.
Multiple PCI ports will be there. X4 is like the max is X16.
Okay. X32 can be there.
X32 can be there.
X32 can be there.
But it is not, there is no devices supporting it. Like not key.
Okay, fine. Okay. So assume that out of 16, 4 lanes are being used. Okay, thank you for correcting. So let's say we have used 4 lanes. Now let us start from the perspective of application perspective. The way we understood the USB protocol, let's again understand from the same perspective. You initiate the application to transfer some data from my laptop into SSD device. Again, the same explanation will hold here. The DMA, that overall thing will still hold here. In this case, what happens is, in my system RAM, assume that this is DDR memory or any other internal memory. Again, there is a drivers comes into picture. The NVMe specific drivers comes into picture. As soon as you initiate the application, processor fetches that, and it doesn't start doing the transfers immediately. I mean, processor will not start performing writes to the SSD device. What it would rather do is, it would create something called as commands. The commands are two types: administrative commands and IO commands. So administrative commands are for creating something called as submission queue and completion queue. There are two types of queues, and IO commands are again for placing the IO. Placing those IO commands like write command, read command, or flush commands will be there. So as part of this memory itself, it will create some queues. I told you, right? The NVMe Express can support up to 64,000 queues, and each queue can have 64,000 commands. Though theoretically this is possible, in real life we don't really do that. I mean, we don't go to the extent of creating 64,000 queues, and probably each queue may not even have 64,000 commands. So what is this queues and commands are essentially? These queues and commands are essentially nothing but some part of my memory being loaded with these commands. In my SSD device, there will be some registers. I mean, the NVMe tells there will be some registers called as submission queue register. doorbell register, submission queue, tail doorbell register, completion queue, head doorbell register. There will be some specific register which will be programmed, by the processor. I mean, processor will initiate a programming to that. Through that, my controller knows that some commands have been loaded into this portion. I mean, into my system memory, some commands have been loaded. So what it will do, it will initiate, it needs to initiate a transfer. Now the question comes, how does this communication happen between my laptop and SSD device? What will be the protocol used for doing the transfers? That protocol is basically PCI Express. Now it could be any generation of the PCI Express protocol. It could be Gen 3, it could be Gen 4, based on what has been targeted for the SSD device. Now let's again quickly understand what we are talking about. Our whole discussion started with we connecting a SSD device into my topology. As soon as you connect it, till the time enumeration happens, everything is same as PCI Express. I mean, in PCI Express, what happens once you have connected the device? I have a PCIe root complex here, into which my the SSD device being connected. As soon as you connect it, the PCIe related drivers will start assigning the bus device function numbers. It will do the bus device function numbers. So the first thing that happens is the SSD is connected. Once it is connected, my PCI root host starts doing the enumeration. I will, okay. No, I will still use it for another 1 minute. Okay. So what happens is, as soon as you connect it, it will assign bus number, device number, and function number. Then till the time the information exchange happens. See, this device will have something called as, in PCI Express there is a concept called as configuration header, which tells everything about what is this device is about. Okay, that information needs to be read by my host. It is like I am manufacturing a pen drive, let's say SSD device. I need to tell about myself. I mean, what is this? Myself means about my device. How do I tell about my device? There are two ways I'm going to talk in this context. One is called as configuration header. My SSD device is going to have one configuration header space. Along with that, I will have a NVMe controller implemented into my SSD device, which will also have some registers. So these are the two things. So the very first thing, once I connect my SSD device into my system, the first thing that happens is my host needs to get that whole configuration header information from the device. So for that, it cannot directly start doing the transfer because it has to go through something called as a link need to be set up. The link that we are talking here need to be set up. So for that link to be set up, the PCI Express physical layer comes into picture. There it has got something called as LTSSN. It goes through various states like detect state. Have they detected each other? I mean, the receiver of this and the receiver of the other side, have they detected each other? Then they go through some states called as polling, where they poll each other. Are we able to respond to each other? Polling means, then there is something called as configuration, where they decide how many lanes are going to be active in this case. Finally, they enter into something called as L0 operating state. So what happened? You connected the device. Very first thing that happens is the device detection, then polling, configuration, and where the link enters into operational state. You see here, as of now, we are not talking anything about NVMe Express. Once this whole thing happens, NVMe Express comes into picture. So, so the physical layer tells to the upper layer, that is the upper layer is data link layer, that the link has been set up. Now you can start your work. What data link layer does is, it does something called as flow control, where it exchanges the credit information. I mean, how much space do I have? How much buffer space do I have to receive the credits? And even the other side tells how much buffer space do I have to this link, right? So that is called as flow control. Once this flow control is done, it is flow control is done on a specific to virtual channel basis, VC0, VC1. The PCI Express supports 8 virtual channels. So I still need to correlate. I mean, in NVMe technology, do they use all virtual channels, or is it specific to one virtual channel? I'll be updating on that portion. So once this virtual channel is set up, then the control goes to transaction layer. So the first thing that transaction layer does is, now that link is set up, at least virtual channel 0 is set up. What is virtual channel 0? I'll explain, because virtual channels are essentially nothing but the buffer space only. There is, virtual channel means a non-existent channel connected between my host and the device. So so the responsibility of physical layer is to make sure that the link is set up. Whatever physical link we have connected the host and SSD device, it is to make sure that the link is operational. Let's say it is supposed to work at 8 gigabits per second, giga transfers per second. That link setup ensures that you can send the data, the PCI Express TLPs, the transaction layer packets, at 8 giga transfers per second without any issues. That is what link establishing ensures. Once you have done, the second thing that happens is the data link layer comes into the picture. What is the responsibility of data link layer is to make sure that it knows how much buffer space this side has to for me to send the packets, and this also tells to this side that how much buffer space do I have for you to send me the packets, because we don't want a scenario where you start sending the packets and other side don't have space to accept the packets. So that is called as flow control. Okay, as soon as the link is established, the next thing that happens is what? Flow control. In very simple terms, flow control means how much buffer space I have, how much buffer space I have, they exchange with each other. Once it is done, flow control has been initialized for one of the virtual channels. It needs to be done for at least mandatory to do for virtual channel 0. So there can be 8 virtual channels, virtual channel 0, 1 to 7. So it is mandatory to do for virtual channel 0. Once it is done, it indicates to the upper layer. What is the layer above data link layer? The transaction layer. It indicates to the transaction layer that link is up, virtual channel has been initialized. So now, what is the first thing the transaction layer does is, it needs to get all the information about my SSD. It needs to get all the information about my SSD. Let's say Western Digital is manufacturing SSD. So what they will do, the first thing, this SSD will have something called as configuration header. Configuration header at least needs to have 256 bytes of information, at least. Other than that, it can have something called as capability registers, something related to the power management capability, interrupt capability, virtual channel capability. So there are various types of capabilities. I think there will be 15 to 20 types of capabilities will be there. So the configuration header is nothing but a memory space which is pre-programmed by the company. Let's say in this case, the Western Digital would have pre-configured that configuration header with a known values. What is the company name? What is the vendor ID? What is the type of device? Everything you will get to know from that. So what is the first thing my root complex will do? It needs to know what type of device is connected. So how does it do? It creates something called as configuration read packets, configuration write packets. It generates a type of TLP called as configuration read and configuration write. As part of that, it reads that whole configuration header information. Uh, Going forward, we'll talk about what is configuration read. I mean, how much data can it read? So it initiates a series of configuration reads. And the medium used for that configuration read and configuration write is what? The 4 lanes that we have used for connecting these two devices. And those 4 lanes are working on what? PCI Express protocol. So once I have performed the read, that whole configuration header has information has come to me. And see, it need not be, see, there is a concept where I can connect 10 SSD devices into my laptop, right? It is possible, right? I mean, as of now, I have only one SSD device, and there may be a possibility where I could connect multiple SSD devices. So how does my system know what is the mapping of this one? What is the address mapping of that? So in return, once you have done the configuration reads, there is something called as configuration write happens. where there will be something called as base address register inside in my SSD device as part of the configuration. So this my host configures that base address registers as per the memory mapping. See, once you have connected your SSD device into the system, there is a mapping that has been given to it. Like let's say the base address is 132TH 170 slots. That will be programmed into my bar register. So by end of this configuration, what happened? Link has been set up, virtual channels has been initialized where they know how much space is available in both the sides. The third thing that has happened is by means of configuration TLPs, configuration write TLP and configuration read TLPs, both have exchanged their information. Now the overall system has reached a point where we can initiate the applications. Till this point, you can't do any applications. I mean, you can't do any actual data transfers. Till this point, what has happened? I have only read the information about my configuration space. Okay. Now comes the second aspect. The second aspect is every SSD device would have an associated NVMe controller. So NVMe controller, as I said, can be two types. One can be administrative controller, or one can be IO controller. So each controller comes with the registers. There are not many registers. I think hardly 20 registers will be there. As you increase the number of queues you want to support, that registers will increase. Let's say for every queue, you need one pair of registers. One for submission queue, one for completion queue. Queue is a very simple concept. Probably at the end of it, you will realize that NVMe is not as complex as it looks to be. Now comes the second part. Now that everything has been set up, we need to initialize the application. What is an application? We are talking only two things we can do in application. What can we do? Either you write data into SSD or read data from SSD, or probably erase or something, right? That might be the third application. Let's say. Let us say we want to write some data into the or read some data. Let's take the second aspect where we want to read some data from the SSD. And there we'll try to correlate where does PCI Express comes into the picture here and what is NVMe here. NVMe, as per me, is not a protocol. I mean, it's kind of a technology which tells how this should happen, but the medium for that whole thing is PCI Express. Okay. Till this point, any questions? Or you want me to repeat anything?
Sir, in the diagram, maybe where does memory come into picture? And buffer space is a part of memory, or it's a separate memory?
I will tell you that. I'll tell you now.
Configuration.
Let me explain all those things. Okay. Basically,
the three things you mentioned. So where do they stand? I think that they are part of memory, or they are part of PCIe somewhere.
I will tell you that part. Okay. Okay. Basically, my system will have system memory. That system memory can be DDR memory, or it could be some other type of on-chip memory. Two types, assume. Okay. Uh, Now, let's say we initiate an application where I want to read some image file. Let's say I want to read same 4 megabyte file from SSD into my system. Let us start that as a specific application. So where does it start? Does it start at hardware level or does it start at driver level? Even before driver, it started at the operating system level, right? Through the Windows OS, you have initiated the application. That application connects with the firmware and that converts it into a series of register write reads. In this case, it's not register write reads actually. I'm sorry, confused. It would convert it into series of IO commands. Because you want to perform a read, it would create a read type of NVMe command and place it into my DDR memory. My processor, what it will do? It will, based on the instructions it got from the firmware, that I need to perform reads to specific location, and that read command to the processor comes with what is the size of what is the address location where it has to perform a read, what is the size. I think when we go deep into the read command and write command, we'll understand each command will be 64 bytes in size. Each command I'm talking about, write command, read command, or even administrative command, everything is 64 bytes in size, and there is a proper decoding of what is each byte means. So which we'll talk when we go deep into NVMe space. In this case, you just understand that to read this 16 megabytes of data, my drivers have translated that 16 megabytes into series of IO commands which are of type read type. What my processor does, processor loads the commands into my DDR. Let's say each command can read you 4 kilobytes of data. Each command can result in reading of 4 kilobytes of data to read 16 megabytes of data. How many commands may be required? One megabyte is 1024 kilobytes. 1024 into 4, right? 16. So it would translate into 4000 commands. What it will do? It will choose one specific queue. It will one of my processor will choose some portion of the memory. What it will do? It will do back-to-back IO commands into that region. How many commands it will issue? 4000 IO commands it will place. Now to place one command, which is how many bytes in size? 64 bytes in size. How many locations will be used? Assuming that my memory is byte addressed. My memory is byte addressed. Each command will take 64 address locations. Here we are talking about a byte address memory. To place one command, I will use 64 address locations. To place 4000 such commands, 4096 commands, it may use 4000 into 64. Some space it will use. That information it needs to tell to my NVMe controller. It needs to tell to my NVMe controller that I have placed some IO commands in the DDR memory. You need to go and process those commands. My NVMe controller has a simple two registers, what is called as submission queue, doorbell, submission queue, tail doorbell, completion queue, head doorbell. Okay, it programs that register. It is not going to be one register. If I have 5 queues, I'll have 5 sets of such registers. For each queue, one submission queue register, one completion queue register. It is called as doorbell. Doorbell, as you know, I mean, it's an indication that I have come in, right? I'm coming in. So it is also processor by programming that register. It is indicating to NVMe controller that you have to process the IO commands. As part of that programming, it tells what is the last location to which command has been placed. It tells the tail. Actually, it's called as tail doorbell. It doesn't tell the head. It tells the tail because already previously it has told to which it has loaded. So previously whatever I have told, now what I am telling, the difference is the commands I have loaded recently. Right? That much is the difference. So what is that I'm talking about? That 4000 commands, each of having 64 bytes. What my NVMe controller does is it will issue reads to this DDR and fetches them continuously. The command, each command is 64 bytes in size. That will tell to my NVMe controller what is to be done. As I said, there are 3 mandatory commands that need to be supported. 3 mandatory commands. One is read command, one is write command, one is flush command. These are the 3 mandatory commands. In this case, since we wanted to perform a read, my host wants to perform a read from my SSD. This command would indicate that you read and give the data to host. This whole communication exchange happens in terms of the PCI Express packets. There is nothing like NVMe signals. There is nothing like NVMe packet or anything. Where is NVMe coming into the picture? This technology where it allows us to create 64,000 queues, where it allows us to create commands, and where it gives us option to create various types of commands, and the concept of submission queue, the completion queue, all this is what is NVMe technology is about. What is PCI Express is all about? How this, see, we have 2 different entities. One is this side, one is this side, which are connected to 4 wires, transmitting wires and 4 receiving wires. That how does that packet exchange happens? For all that we use PCI Express. So it would definitely, since my device is interacting with memory. So when I have to read the IO commands, how many IO commands I need to read? A bunch of IO commands, right? I mean, which is much bigger than, because I said 4000 into 8, which is 32,000 bytes. My NVMe controller issues a memory read, to this address space to read all those commands, and it starts processing. Now, since I am performing a read, I need to give data back to my device, right? I need to give data. Again, to give the data also, what I'm going to frame? My NVMe will frame a memory write request. It fetches the data internally. It creates a completion packet, or it creates memory write packets with payload, and stores the data into specific location. Again, there also where it will store one portion of my DDR. It could be one some other part of the DDR. Once I have done it, I have processed my command, right? Who has processed? NVMe has processed command. So how does it indicate to the processor that I have, how does it indicate to the host that I have processed these commands? That is where comes the concept called as completion queue, where it loads the completion queue, indicating that whatever commands I have taken, I have processed it. Through that, it knows that my host will get an indication that there is some memory location where it, through which, by polling that, my host knows that completion queue has been updated. By seeing that, it knows how much portion is valid as part of my memory, and then it can be used for further purpose, right? So this is how the overall thing is happening. Now, for someone working into NVMe, why PCI Express is required? Because it all starts with PCI Express, right? The whole connection, it starts with PCI Express, where you need to understand how the link gets established, right? What is the concept of, what are the various states in the link connection? Like when we say detect, what happens in the detect? When we say polling, what happens in the polling? Or configuration, what all aspects are configured? How do we decide the link speed? uh, all those aspects, and whether lane polarity inversion, everything. Then in L0, what happens? Let's say some error happens. So how does it recover from the error state? And when it comes to power management, what is the significance of low power states like L0s, L1, L2? All that need to be understood, because even though it's a SSD, it's a PCI Express based SSD. That's how we have to understand, with NVM flavor added. See, normal PCI Express devices, there is no NVMe controller. Normal PCI Express based devices, there is no NVMe controller. It just can understand the PCI write reads and decode it. But when it comes to SSD based device, there is an additional controller which is coming into the picture, which is getting all the commands in terms of PCIe based commands. It could be configuration write, configuration read, memory write, memory read. I believe those should be sufficient, and I don't see any IO need for any IO read, IO write, and IO read, because IO in PCI Express there are four types of commands, four types of TLBs. One is configuration write and configuration read. Second is memory write, memory read. Third is IO write and IO read. Fourth one is the messages, actually, for generating the interrupt, for generating some broadcast messages or low power messages. We use messages. IO write read won't come into picture because they were mostly targeted for the legacy devices, legacy PCI Express based devices, where we wanted to support the PCI capability. I think when I get into the presentation, you will understand more about those aspects. Did everyone? Did you get the feel of how PCI and NVMe are connected to each other?
So you mentioned about link, right?
Yeah.
It's a four values. It's a four link.
It's,
so what does the link consist of?
Sorry,
What does the link consist of?
it consists of 4 transmit lanes, 4 receive lanes.
Four transmit lines and 4
receive lanes. Yes. Any question? No, if you feel something to correct you, please feel.
No. Okay. So actually need some time to digest this much of data. So I just want to come on some basic conclusion which I extract. So am I right if I say PCI is a interface and NVMe is a protocol?
NVMe is not a protocol; it's a technology, I would say.
NVMe is technology where PCI is just an interface.
It's an interface through which NVMe technology has been implemented.
Okay. So the question is, if it's just an interface, so can I change interface uh, to just like we have SATA and we
That's
have.
what in fact is.
So can I implement NVMe with SATA instead of going with PCIe if I just want PCIe lane 1?
NVMe.
Because it's just interface, I can change it, right?
No, one second. Can we change it to SATA? It is technically possible. It should be doable.
Okay, it's doable.
You want high bandwidth. That's why you go with PCIe.
No, if you ask me, is it possible to do? It is possible. Because at the end of the day, what is that you need to do? You should be able to read the commands from here,
That's what
and
my
you should be
question
able to
was.
process the command, and you should be able to send the data.
So NVMe can be implemented with SATA. Obviously, SATA 3 is 6 Gbps and NVMe is 8, so performance will be little low.
No, not little low, significantly lower. Actually. See, what is the difference
6
here is-
versus 8, right?
No, it's not about 6 versus 8. See, it's 4 lanes. Because of 4 lanes, you get
See,
4.
I'm talking about
1 lane. Okay.
X1 only.
Okay.
So I have a controller with NVMe X1.
Yeah.
So I will be using PCIe X1.
Yeah.
SATA is X1,
Yeah.
right? SATA highest is 3.0, which is 6 Gbps.
Okay.
One lane is PCIe Gen 3 is 8 Gbps. Will I get only that much of difference, 2 Gbps,
No, it's
or it
more.
will be
It's more
entirely
than that.
different?
It's more than that. Because see, SATA, as I understand, it supports only one queue, where into the same queue you place the commands.
Then,
Yeah. So again, I'll tell you, the NVMe has a more concepts than that, where you can divide the overall thing into
there I was coming.
namespaces.
There I was
Namespaces.
coming. SATA will have its own set of instruction set, and so if NVMe required some queuing and all, how we can implement it? That was my question actually.
Okay.
It's not just a connection.
Yeah. Yes. I mean, if you go down to that level, then PCI Express is the one thing which can address. Any other questions? I mean, now I would be going into the PCIe basics. Before that, if you want me to repeat or if you have any specific questions.
So what you showed here is the read part, right?
Yes.
How about the write and what are the things that vary in the write scenario? When you want to write something from host to the device.
Okay.
One meeting, right? Yeah. One meeting. Yeah.
Please.
So how are the things in case of write?
In case of write, okay. Write would still involve transferring some data from my RAM to my DDR into my SSD, right? And that has to be initiated by NVMe only. That has to be initiated by NVMe only, and it has to be done through IO commands only, right? What is IO commands I'm talking about? When I say IO command, I'm talking NVMe IO command. And who has initiated that IO command? Processor has loaded that IO command into my DRAM, and once I ring the doorbell, submission queue doorbell, my NVMe fetches that IO write commands, the write command, and figures out that there is a write need to be performed. That write could mean I need to transfer some portion of data from here to here, right? And the PCI Express, the best thing about PCI Express is each connected component itself can act like a bus master. There is something called as full bus mastering, where this itself can act like a bus master, and it can perform a read from here, and it can transfer. Is that
SATA is like NVMe is an enrolment from SATA. So it is like how does it is like SATA, for example, it is like maximum it can go up to 6
Gbps or maybe 12 months.
Yeah, 12 months. So NVMe is kind of an added advantage compared to SATA. So why to link in SATA to an NVMe?
You're asking why?
I'm trying to address Abhishek's question. So the main thing is like when you have an interface, right? Then, for example, as SSD product, you have a SATA product. When you want to directly connect to a PCIe slot or a SATA slot, you directly interface with the SATA itself, PCIe to SATA. Why we want to have another interface to speak to the PCIe slots?
I was just
No,
asking.
please. Sorry, please.
I was just asking for understanding ki is it interface versus protocol or it is something else?
Okay. Any other question?
This NVMe is it's a chip or it's a controller or it's like hardware is there or just software?
No, NVMe has the controller also.
Discussion is there.
No. NVMe has a controller. See, it's a, you can divide. If I say SSD device, like in USB based devices, if I am purchasing a pen drive, it will have USB core. It will have a USB core, and the remaining is the storage part of the pen drive. In when it comes to SSD devices, the storage part is SSD storage. What you have here is the logic of NVMe controller. It can be two types of controllers. We said administrative and IO controller. Other than that, the registers corresponding to each controller. That is the hardware portion of it. And I think on the SoC side, on the system side, there won't be any hardware specific to. It's all PCIe topology because I can see the PCIe related root complex and the system memory, everything is common to any.
We can remove NVMe also. PCIe.
We can't do that, right? We can't do that because if I just keep the PCI Express, the PCI Express cannot understand IO commands. It cannot understand the administrative commands. It doesn't understand what is meant by doorbell. That additional logic itself we are calling as NVMe logic. What I was telling is, without this also we could do, but then you can only do, everything has to be initiated by host. Everything has to be initiated by my root complex, all the memory writes and reads. Whereas here what you are doing is you are reducing the load. See, processor is giving all the load to NVMe controller. How does it do? It just loads commands into the RAM. It just loads the commands into the DDR, and it tells to the NVMe controller that you go and fetch those commands and process those commands. All that. Now what happened? Till the time it is processing those thousands of commands, processor is free, right? It doesn't have anything to address with NVMe because they have established their own path. They have established their own path, and it can do both write and reads and initiate the data transfers to my system memory. Once this transfer has been initiated, my NVMe controller, which is sitting in my SSD device, need to tell to the host that I have done with it. For that, it has got something called as completion queue. It loads the completion queue, saying that these commands have been completed. Now, please.
No, with comparing it to USB, I mean, I think USB you said it's only host initiated.
Yes.
But here it is like both ways it is initiated. Is it? That's what you're trying to say?
No. Still, see, here also it's still host initiated only.
Yeah,
See,
that's what I want to know.
yeah, unless my processor doesn't program the register here, it can't do anything, right? I have to ring the doorbell. I have to program the doorbell register. Only then it knows that now I have to go and fetch the commands. Where does the advantage of NVMe comes into picture is, earlier in SATA protocol, SATA SAS protocols, it was only one queue where you can load only limited number of commands. It was limited by the hardware. The SATA protocol itself is limited by the hardware implementation. Everything was implemented into hardware. Here, we are using the DRAM to load all my commands, and NVMe can process multiple queues concurrently.
So I think where you're coming from is you're looking from the USB mode. How does your USB interact with your memory, non-volatile memory, right? And here you're trying to understand how does the NVMe come into picture when you have the PCIe interaction with it. So USB has your whole mass storage controller protocol and your SCSI controller. In the PCIe side, we do not have it. I think the NVMe has been developed as a technology for you to have the interaction with your memory over PCIe. Earlier, for your memory, you already had SATA. So for PCIe, you do not have that. That's why you have the NVMe technology.
But I'm understanding it's the main controller which sits in the.
Yes, exactly.
It's the main controller. It's
Yes.
the
So you have the PCIe as hardwired signals, link and all that. But you use your NVMe technology to communicate with over the PCIe for the
So
moreover, does it works as a DMA controller? Like,
which one?
like
Yeah, NVMe controller is more acting like a DMA controller.
So there's no internal DMA within the host to actually.
Host won't require DMA in this case.
How about the 5?
5 will be required.
So the data from the DRAM
Yeah.
will be directly given to 5. And
No. Basically, there are two types of interactions that can happen here. Okay, one is the first thing. Let's start from the first point. I'll keep it quick because I want to redo everything. It may bore many of you. The first thing it happened is link established. The flow control has happened. Okay. The third thing it does is the enumeration. What is enumeration? The concept of reading the device information. I have, let's say I am manufactured a device. I need to tell to the world that what is my device is about. So what is that I did? I have loaded my configuration header. The very basic size of configuration header is what? 256 bytes. And based on more capabilities I want to support, its size can be bigger. Let's say it is adding up to 356 bytes, for example. I need to, my host needs to know about my device. As part of that, what it will do? It will do configuration reads. For that, it will use the PCI Express protocol. Okay, there what is happening? I am issuing a configuration read and getting the completion packet with the data. That is one exchange that is involved. Second thing that is happening is once this enumeration is done, it informed to the, the drivers are updated that enumeration has been completed. So I know everything about what is the device connected. I know that this is the name of the company, this is the size of company, this is the vendor ID, everything I know. And I also know how many virtual channels does it support, what all traffic classes are supported, everything I know about the connected devices. Those people who are new to what is virtual channel, what is traffic class, please don't worry, because we'll be starting, this is more like a bigger level picture of what is PCIe, what is NVMe. We'll be starting very much from the fundamentals. So that's the first information exchange that happened. So second thing is, now the device is in a state, the connection is in a state where we can initiate the transactions. That is where application comes into picture. As soon as your application came into the picture, we have loaded this with commands. Loaded with this command. Now what is the second interaction that is involved from here to here is, I need to program the registers which are sitting here. How do I program those registers? I believe it should happen as configuration writes only, because configuration writes. And their little confusion is there. Because it the spec doesn't clearly mention it should be configuration write or memory write. What they say is it has been mapped to bar 0 bar 1 address register. I believe it should be memory write. If I understand that at that level, if it is mapped to bar 0 bar 1 registers, those register space, it should be memory write. So my root complex will initiate memory writes to this space to program the registers, because there is nothing like APB protocol or there is nothing like AXA protocol. Everything has to happen through the 4 transmit lanes, that 4 receive lanes. So I will program the registers inside that. Once it is done, the third part of this will be IO commands have been loaded that need to be informed to NVMe controller that now you have to process the IO commands. Here the biggest advantage of NVMe is that my processor can set up thousands of such queues, and it can program thousands of submission queues concurrently by writing, and it can start reading all those thousands of queues concurrently. This is where the major difference comes from SATA to NVMe, where a multiple concurrent process can be running, where my storage space has been divided into multiple spaces, where each of them being loaded with one concurrent command.
So once we go through the details of the protocols, there should be flow diagram for memory writes,
yes,
for writes and reads.
Yes. So this is the third end. Yeah.
Just one very related discussion. So you are saying the host is going to write the configuration space, right?
Yes.
But what is need of it? Like typically on PCI, if I know correctly, usually the configuration space is fully written, right?
Mostly the bar register need to be written. Bar, there is something called as the bar 0 bar 1 registers that need to be written. Or once we get into the basics of enumeration, you will understand that the configuration header will have 2 types of spaces. One is read-only space. Second is fields that can be written. One of that examples is bar registers. What is the significance of bar register? Is processor will program the bar register with the base address assigned to this SSD device. See, once I connected SSD device, I need to tell to my device that this is the address mapping assigned to you. That will be programmed into my bar register. So their configuration rights will come into picture. So that's the third thing in what, right? The fourth thing is the data transfer, right? I may have to write the data and we have to read the data. Again, I will use the PCI Express medium for that. Again, the repeating the same thing. The biggest advantage of NVMe is the ability to process concurrently hundreds of queues or many sets of command queues concurrently.
Sorry to ask again. So what's the purpose of that configuration, right? Is it to identify the device?
No. Configuration read is to identify the device. See, 256 bytes are there. Each configuration read can read 4 bytes.
Yeah, so it tells about the device, right? It's
Everything.
about the device.
Yes.
Configuration header
Yes.
tells about the device.
Yes.
Now the host is writing something.
Host is writing something. Yeah.
The configuration you mentioned about the bar register.
Bar register. Bar stands for base
But
address register. Yeah.
It's actually a PC address space, right?
Yes.
So why the device needs to know the PC address space?
It needs to know because when a transaction comes to it, it will figure out whether the transaction is targeted to it or not. When a specific transaction comes to it, it can figure out whether the transaction is being targeted to that device or not.
So for that we'll have the some different device handling. Why do you have to use this address data?
No, because memory writes and reads will be targeted with the address section. See, when you do the memory write TLP, you keep the target address in that. You keep the address in that memory write TLP. I think that can be used for that. But I'll check and come back to you. I mean, your question is, why do we need to program the bar register with? I mean, why should we program
PC
the
address space?
yes PC address space? I'll check and come back. Any other questions?
So in this course, are we going to deep dive into how the link is created and if there is any error, how that is to be troubleshooted?
Yes, all those things. So, with this understanding, let's get into the PCI Express concepts.
Quick time check, half an hour.
Sure. Yeah. So one thing is, even though I'm starting with PCI protocol, this session is supposed to be like a bigger level picture of PCI Express protocol. When we start the training after 1 or 2 weeks, we'll be starting from the basics of. Basically, we'll be taking one simple on-chip protocol, one simple peripheral protocol, like APB protocol and SPI protocol, something like that. Through that, we'll understand the basic concept of communication. I mean, my understanding is that many of the people who are attending are the interns or freshers who don't have much understanding of what is protocol, what is a transaction, all that. So I'll be spending 1 or 2 weeks to give you a brief about one on-chip protocol. It could be APB protocol, what is transaction means, what is handshaking, and then we'll be taking one kind of simple SPI kind of protocol, and through that we'll be understanding how peripheral protocol work. I mean, how does uh, the timing diagram look, what are the signals involved, how do they differ. Then we'll be moving into PCI protocol, because in this session I don't want to teach all those basics. I wanted to give a bigger picture, but those who are uh, going to attend the main training will be starting from the very much from the basics. So let's start with the PCI protocol overview. Basically, what is a protocol? Guidelines on how the various phases of transfer happens. I mean, when we say protocol, what is meant by that? It's all about data transfer, right? There is a data transfer happening from host to device and device to host. The protocol gives us the guidelines on how those data transfers, various phases will happen. A protocol also provides the signals to implement those phases. Okay. I think this all I have already explained various types of protocols. We have already talked about advantages of on-chip protocols, and we just took a brief overview of what is a skew means. I'll be talking more about skew later. I mean, there is two types of skew. One is data skew, one is clock skew. How PCI Express is going to address this skew concept, we'll discuss. I mean, when we go deep into PCI, there is something called as deskew mechanism in PCI Express. What is skew means? The variable time difference when the signal reaches to the destination end device, right? There can always be the difference build up. To address that, what we do is called as deskew. To address the skew, we do deskew. To deskew, PCI Express has some special type of packets called as skip order sets. Using that skip order set, it does the deskew. When we go to that specific topic, I'll be talking more about it. Let's start about how PCI Express has evolved, because everything before that was all same thing that we discussed in the previous session. Okay. Now let's talk about how PCI Express has evolved. Actually, PCI Express has evolved from PCI and PCIX. There is a big difference between PCI and PCI Express. Actually, what is one of the major differences? PCI is a kind of parallel communication protocol, where the information is sent in a parallel manner, address, data, everything written on a dedicated lines. PCI Express is a serial communication protocol where all the information is transferred on a same set of common lines. So there's a difference. Now you may say, how can we create a serial communication protocol from a parallel communication protocol, right? PCI and PCIX has some concepts like configuration space, the concept of configuration header, the concept of enumeration, the concept of full bus mastering. There are few things which are uh, there in PCI which have been taken. Uh, Initially, the concept of PCI is, what is PCI stands for is, so PCI, as you see, stands for peripheral component interconnect. PCI X is the purpose of PCI Express is also to do the peripheral component interconnection. So if you see, at the end of the day, our idea is to what? To connect the peripherals into the system and to do the transfers. So as part of that, they have some techniques that are already adopted in PCI. Something called as having a concept called as configuration header, type 0, type 1. The concept of base address registers. All those concepts have already been taken from PCI and adopted in PCI Express. So that is what I mean by PCI Express has evolved from PCI and PCIX. What they tried to do is, whatever positives that are there in PCI and PCIX, they have taken, and whatever negatives there. What is the negative with the PCI protocol? It's a on-chip protocol. The concept of clock skew, data skew, they're all problem, right? And they're limited by frequency of operation. Then they figured out why is the limitation coming. The limitation comes because of the parallel nature. Then they removed that parallel nature. So they took all the positives, whatever drawbacks that were there in PCI. The drawbacks majorly are coming due to the parallel nature of the protocol. They removed that parallel nature. So what they got is the PCI Express. Okay. So PCI, as you see, stands for peripheral component interconnect. PCI is completely different from PCI Express. I mean, they should not, as a protocol, they are different. Need for PCI. See, take any computer system. How to summarize the computer system? I mean, any system is what? A processor connected to various peripherals, right? Connected to each other using motherboard, right? I mean, you have motherboard to which everything has been connected. So that is where PCI has been developed. But then they saw that there is a limitation in that. I mean, they were not able to hit beyond 4 gigabits per second. Let's say whatever best PCI you could take, PCIX was an advancement of PCI. They were not able to go beyond specific bandwidth level. Let's assume 4 gigabits per second. But the current application requires us to do in much higher speeds, right? That is where they needed a new approach. Again, that's where what they did, they took the best of whatever is required from a peripheral component connection perspective, they took, and they converted the protocol into serial nature. As soon as they converted the protocol into serial nature, the frequency of operation could be anything basically. See, right now we are talking about 64 giga transfers per second for the PCI Gen 7 or previous generation 32 giga transfers per second, right? So at that, I mean, because of serial nature, you could work at theoretically any speed. So that is where they were able to take the best of the both the things. Like they were able to take the best features of PCI, and they were also able to take out the limitation of the speed. And that's where we are able to hit the whatever required bandwidth we need. So it requires interconnection of all the components. There was a need for a protocol which helps with this interconnect. So that is PCI. That is where PCI came into picture. What is PCI? It's a peripheral component interconnect. All computer peripherals connected to interconnect. So we have an interconnect to which all peripherals have been connected. PCI specifies the guidelines for peripheral communication. See, what is the bandwidth we can get from PCI is it can work at 33 megahertz. Since it's mega, I've taken 10 to the power of 6 factor, and the bus width is the data bus is 32 bits. So you can maximum get 132 megabytes per second. If you convert this 33 megahertz, 32 bits per second, you get 132 megabytes per second. If you compare with the speeds we are talking about in PCI Express, it is significantly lower. Uh, One of the features in PCI is a concept called as full bus mastering. What is full bus mastering is all the components connected to the interconnect can act as a masters. They can initiate transfer without processor intervention. Let us now understand what is meant by full bus mastering. If I have an interconnect with multiple devices connected, generally in a non-full bus mastering system, it is the processor which has to read from specific component and perform a write to specific component. That is how we would understand it. Whereas with the concept of full bus mastering, there is a DMA concept associated with each peripheral. What it can do is this can become a master, and it can initiate a read to this and read the data without much of processing intervention. Of course, processor will be required to tell that you need to read from here, you need to store the data somewhere here, let's say. But it has a one important concept called as it can initiate. I mean, processor will only do the register configuration to tell that now you go and read from here and put the data here. Okay, that concept is called as full bus mastering. All the components connected to interconnect can act as a masters. They can initiate transfer without much of processor intervention. I mean, ideally what we are achieving out of it, we are reducing the load on the processor and we are moving that whole thing to the individual components in the architecture. And they support burst mode. But what is burst transfer means? The data transfers to the continuous locations. You issue one address space and you can issue multiple data transfers related to same address location. And PCI has address and data bus shared. It uses a concept where it try. Why do you think we want to do the address and data bus sharing? Can someone this point where I'm talking address and data bus shared? Why do you think we want to share address and data? To reduce the number of pins, right? I mean, see, PCI supports a concept where initially you initiate the address phase, then the data transfers corresponding to that transaction will happen. So at any point of time, either you are doing address phase or you are doing data phase. So to reduce the number of pins, we can use the address and data bus. Why we need to reduce? Can you tell me? Because PCI is about connecting the external peripherals, right? You want to reduce the number of pins that are there with the peripheral device. I mean, let's say we have a 32-bit address bus, 32-bit data bus. It essentially becomes 64-pin slot, and we need to connect 64-pin slots into my motherboard. Whereas by sharing address and data bus, instead of 64, you still have 32. So that is what advantage we can think of, right? And PCI does not have physical layer or file. Why? Because at these speeds, you don't need any special unlock circuitry to work at 33 megahertz or even 66 megahertz or that speeds. You don't need any special unlock circuitry.
Is there any limitation because of this full bus mastering where each component can talk to each other? Do you lose the control in the system? Or is there
No,
some
there won't be
disadvantage?
any limitation because at the end everything is controlled by the processor. At the top, it is a processor which is telling, even for a master to initiate the transfer, processor tells now you go and read. Right?
So that concept is applicable only when you have multiple SSDs.
Multiple.
multiple devices connected.
Yes.
If there's only one SSD connected to the port, then that doesn't work.
No, point is it has a feature. Whether you want to use that or not is a different thing. The PCI as a protocol supports full bus masking. Whether there is no need to.
And is there okay, limitation would be the number of ports that you have in the. I mean, when it comes to number of devices that you can connect to the PC.
No, it's not the actually number of. It's not the number of ports. I will tell you. It goes down to a little bit about electrical concepts. I mean, once you connect more devices, let's say imagine I have a one gate and gate. Here I'm connecting multiple gates. Tell me, as I increase the number of gates, what will happen? To this point, can you tell me?
It will load.
Load will increase, right? I need to provide more current to this, more current to this, more current. I mean, as I increase the more gates connected here, I will have to provide more current to drive those things. That would definitely impact the signal level here. I mean, I won't be able to drive, the transitions will not happen quickly, as I can see. So that is where the limitation comes into picture. How many slots can you connect? 4 to 5 slots. Use expansion slot to connect more peripherals. I mean, given one interconnect, you can connect maximum of 5 PCI devices to that. Now you may be thinking, what are we talking here? I mean, what we are doing here is we are setting the base for moving to PCI Express. We are trying to understand the positive aspects of PCI. We are trying to understand the drawbacks of PCI, and we will figure out what are the drawbacks. For example, the load is the drawback. Why load is coming into picture? You are connecting multiple devices to a point. So what PCI Express does, remove that whole concept, make it point to point. What PCI Express does, don't connect multiple devices to a point, just make all the connections point to point. Then there is no concept of load itself, right? I mean, you just have to interact with one device. So this is one. The other problem we are facing is with what? The speed of operation. Why we couldn't go beyond 33 megahertz, or why we couldn't go beyond 66 megahertz? Again, the timing closure and all that problem will come into picture. Then they figured it's all coming because of the parallel nature of the protocol. Then they said, let's move to serial. Okay. Then they had to share address and data bus, all that, because they had to reduce the number of pins. Then again, that problem can be solved by what? Moving to serial nature. They could reduce the pins and they don't have to worry about the timing closure. So that is the reason, that is where we are coming actually. If you ask me why we are starting with PCI, PCI Express is evolved out of PCI. So we are trying to understand the good aspects and the drawbacks, and we'll try to address those drawbacks. So then what we get is PCI Express. So because of that load, as the frequency of operation increases, load reduces. Then it has got a concept called as arbitration. Arbitration is coming into picture because there are multiple devices connected into the same interconnect. So you need to decide who is going to do the transfers now. So component issues a request. There is an arbiter which is present in PCI interconnect, which issues the grant. The PCI device sends request for interconnect and arbiter gives grant. Now PCI Express won't have this concept of request grant mechanism, but of course it also has something called as a port arbitration, virtual channel arbitration, which we'll talk when we get into PCI. It is limited by frequency of operation since it is parallel communication protocol. Arbiter sitting inside a bridge connected to PCI interconnect. Okay. So I told you that PCI is a parallel protocol. This is what I mean by parallel protocol. What you see here is there is a dedicated line for clock. There is a dedicated line to tell that frame is running now. I mean, starting from here to here, the frame is active. The transaction is active. And you can see that AD means address and data bus being shared. Then you have whether you are indicating whether it's a command or whether it's a data. And then you have instruction ready, T ready, device selection, everything. So everything is being sent on a dedicated lines. There is a dedicated line for it. What makes it a parallel protocol? And as soon as you're sending something with respect to the clock, you're sending something with respect to the clock, your timing limitation comes into picture immediately. I mean, any protocol where you're sending clock separately with other signals, you have an immediate problem with clock skew that immediately limits your frequency of operation, because you will have to close the things with respect to clock. So they figured that clock is becoming a problem. They removed the clock altogether. In PCI Express, there won't be any clock. You won't transmit any clock from host to root complex to the device. Rather, clock is embedded into my signal itself. Whatever data I send, the clock gets embedded. The receiving device extracts the clock. So that's a different concept. There is something called as clock recovery circuit will be there. That way, they avoid this concept of skew. Let's not go deep into it. What is that you should notice here is one address, multiple data phases. This is what we technically call as burst transfers, right? When you have initiated one address space, as long as your frame is active and T ready is there, you're sending the data transfers. So this is what we call as burst transfers. Okay, what are the ports that are there in PCI? Clock, frame end, whatever we have seen in the previous diagram. AD, iReady, T-ready, device select, grant, and address and data bus are shared. Now let's come to the important point, summary of what we have discussed so far. The PCI has a limitation. See, PCI has limited number of slots due to load limitation at specific frequency. At any given frequency, as you increase the frequency, you need to reduce the number of devices connected. I told, right, to the interconnect maximum you can connect 4 to 5 devices. If you feel that no, I should, instead of 33 megahertz I should run at 128 megahertz, then you may have to reduce the number of devices connected. Bridge is the way to increase the number of slots. What do? You connect one more interconnect. You connect both the interconnect through bridge, so that you can increase the load. I mean, you can increase the number of devices connected. Clock is sent along with the data, puts limitation on the frequency. Whenever you send a clock as a separate signal along with your other signals, it always becomes a limitation for you. So important concepts are what? What is the important concept we need to learn out of PCI? It's a processor programmed IO. I mean, processor assigns the IO mapping to each device. You would be aware of the memory mapping, right? Where each device connected into the system has a address mapping. It supports burst transfers. Then it supports peer-to-peer communication through full bus mastering. As I said, now how does this? What is the essential concept of full bus mastering? Is the concept of DMA. The system has a DMA which can be configured to transfer data from one device to other device with minimal intervention from the processor. So the full bus mastering is synonymous with the DMA. I mean, full bus mastering is working because there is a concept of DMA implemented into the PCI system. And then you have PCI configuration space. All device configuration memory is mapped, 4 kilobyte mapped for each device. Let's understand this configuration space. What is meant by a configuration space? Whenever, let's say I am a manufacturer. I am manufacturing one printer and I want to sell it. So once the printer has been connected into my system, my laptop needs to know what is this printer is all about, right? How do they know? So for that, as a manufacturer, I will create something called as configuration headers. Now my headers can be two types. One is the header which is configured for interconnect kind of device. One is for device, because in PCI there are two things, right? One can be interconnect, one can be device. The interconnect, the header that is targeted for interconnect is type 1. The one which is targeted for device is type 0. So I will manufacture my printer with some 256 byte space, where I load the 256 bytes with some values to tell who am I, what company am I, what is my device ID, what is my version ID, multiple things I will tell. As soon as you connect, my host processor reads that whole information and figures out the details about it. I think it goes back to the same thing we discussed earlier for USB also, right? Configuration space is a mix of field. Few are hard-coded values, few need to be configured by the processor. I said that some need to be read, some fields can be written by the processor. Okay. Okay. So this summarizes PCI. Now coming back to the protocols. Okay, now we are actually moving out of PCI and coming to something else. Basically, if you talk of any protocols, let's say you talk of AXI protocol, AHP protocol, OCP protocol, anything. If you summarize all the features in any of this protocol, mostly you'll end up in these features. I mean, a protocol may support out of order transactions. A protocol may support overlapping transactions. A protocol may support cacheable transactions, bufferable transaction, wrapping. Let's not read everything. This slide summarizes everything. PCI Express is truly universal protocol because whatever you see here, some or other way it has got something to support each and everything. I mean, PCIe will have some way to support out of order. I mean, it will have a concept where it can do the transfers out of order. It can probably initiate the concept of cacheable, bufferable, not exactly by the same name, but it can essentially implement whatever you see here. Let's say you want to do interrupt support, it can do. Let's say you want to do error handling. I mean, you want to report an error. Device wants to report an error to the host. The PCI Express will have a mechanism to report that. So in summary, why I have listed, you may ask, why did you list here? What I wanted to explain you is PCI Express is truly universal because most of the things you see here, it somehow supports. Let's say, so our goal over the next few weeks when we do the training is to understand at each stage how these things get supported. Okay. I think I have already talked about full bus mastering, bus transfers we talked, interconnect load also we talked. Yeah, I was talking about interconnect load, right? The PCI based interconnect supports connecting maximum of 5 components per interconnect. Why? Connecting many components to the signal interconnect increases the load of interconnect. As the load increases, load is what? Essentially capacitance, right? As the load increases, the time taken to charge the capacitor increases. Same port need to provide increased amount of current to all the connected devices, because as you connect more devices you need to give more current. To provide larger current it needs larger charge. I mean, to store larger amount of charge it needs larger capacitance. Basically we are talking about the parasitic capacitance, right? There is no real capacitor there. As the capacitance increases, charging takes more time. It impacts the signal behavior. Okay. Now, why arbitration required? I told you, because there are multiple devices connected. You need to choose which device is going to be the master for that interconnect. So for that you require arbitration. Many peripherals are connected to the same interconnect. All of them might want to do the transfer at same time, but only one of them can do. So arbitration helps decide which component will initiate the transaction. Arbitration is required to decide which among them will have the control of the interconnect.
Smooth race condition.
Yeah.
Avoiding.
Yes.
Quick time check. We have 5 minutes before we go to the wrap up.
Okay.
How many you have?
No, I think I'm done actually. I think just wanted to set the tone for the training.
I'm just keeping it so that people have to try
Yeah.
So basically, just to summarize, PCI Express takes the best of the features from different protocols. OCP supports, let's say OCP protocol, Open Core Protocol, supports out of order transaction using a concept called as thread and ID. I mean, some of you who are familiar with OCP will come across a term called as thread and ID. That concept is taken into PCI Express. The PCI Express transactions, you will see that in the header you will see there is a thread field, there is a ID field. PCI supports full bus mastering, which allows any component on the interconnect to communicate with any other component of the interconnect. So PCI Express takes this concept from PCI. So some concept it has taken from AXI. I mean, it cannot be exactly same thing, right? It's the feature that has been taken and implemented into the protocol. Next, PCI Express takes concept of configuration header, enumeration, and address mapping from PCI. PCI Express takes the concept of point-to-point connection from PCI Express. Majorly, PCI Express has evolved from PCI and PCIX. PCI and PCIX are parallel communication protocol, and PCI Express is a peripheral communication protocol. So in this slide, I'm trying to summarize that whatever is the best features that are there in various protocol, it has been taken and that it's been implemented. So with this, we will stop the session. In the next session, when we do, I won't start with PCI, I won't start with USB. We will have a 1 or 2 weeks of time where we take you through the basics training. And those who are already experienced, probably you can skip that. And when we start with USB and PCI, we'll inform you those specific schedules.
Okay, thank you. Any last minute questions? I've just kept 15 minutes. I thought of doing the registration, but I need to have a discussion with him about how the session went, what we need to do next. So I've kept 15 minutes for the time. Any last minute question?
One question.
Yeah.
So you mentioned the presence of clocks makes it a parallel protocol.
No, one of the aspects of parallel protocol is clock is always there.
Because even the serial protocols like I2CSK has the clock.
The speed of transfer is very low. Let's say you are talking about 10 megahertz speed. The skew won't be a problem at all.
Here also like we have multiple devices.
Multiple
The same
devices. Yeah.
But at any given point of time, we can communicate to only one device, right? So one device communicates to other device.
Yes.
So why is the load coming here? Because it comes only when there are multiple devices being communicated.
Multiple device. See, even though you're doing transfer to one device, but other device load does adds up to that, right? The signal may need to be transmitted.
So it means there's no concept of like chip select or something.
There is no chip select concept.
Okay, there's no way to isolate the devices.
Yes. I mean, see, again, I need to.
The line will still be active. The chip will not be active, but the line will still be active if you take the load.
Any other questions?
So what are the speeds supported in PCIe?
PCIe, what are the speed supported is? Okay.
Laptop is
Gen 1 supports 2.5 GT per second. It's called as DP, transfers per second. Why we don't talk in bits per second is because PCI Express can support multiple lanes. I mean, 1 lane, 4 lane, 8 lane, 12 lane, 16 lane, 32 lanes. Because of that, they always talk in terms of transfers per second that need to be multiplied with the number of lanes. Gen 2 supports.
just an idea.
Yeah, I will just quickly summarize here. From here, it doubles.
We have clock in PCIe as well, right?
Clock will be there, but the clock will not be transmitted on
Differential
the.
clock.
No.
Embedded within.
Embedded along with the data bus.
You see PCIe routing, right?
Yeah.
We have PCIe DXRX plus minus lane 1, lane 2, lane 3. So we have one differential lane for clock plus minus.
Plus minus. I haven't seen. Because we don't send clock separately.
There is, okay, we'll see.
Internal to the 5 clock can be there. I mean, where
It is
see
there.
between 5 to my upper layer, logical subclock, right? There can be a clock.
Okay. So if you see PCIe pinouts, right, we have separate differential clock plus minus which we use for NVMe devices.
Okay. Let me check and get back.
All right, folks. I think thank you for joining. We'll send out a notification for the USB and PCI trainings for all the registration. We recorded this thing, so everybody would want to learn everything. But when you have those trainings for both protocols, it may become either too drag or too tiring. What I would recommend